Right, this is the second lecture for Chapter 4, and in this lecture we're going to start looking at precipitation reactions, which is the first of 3 different chemical reaction types that occur in aqueous solutions that we'll be evaluating over the course of this chapter. So the first one we investigate is precipitation reactions, and we have acid-base reactions, and finally oxidation-reduction reactions. Each reaction type will have its own lecture, so it's really nice and easy for you to find what you need while you're studying. Okay, so precipitation reactions are really interesting. What you essentially will have in every precipitation reaction that you're asked to evaluate is the combining of 2 aqueous solutions and a precipitate is going to form. Right? What is a precipitate? A precipitate is just a fancy name for a solid. So in each one of these 4 test tubes, we have the product of a precipitation reaction. The name of the precipitated product is just beneath the test tube. And for each of these reactions, you would have had 2 reactants that were homogeneous solutions, right? So mixtures that do not have distinguishable parts. You combine those 2, and all of a sudden you have this solid that crashes out of solutions. You can think of it as like snow falling. So it falls out of solution. So you have this separation of things that are in a liquid or aqueous phase and those that are solid. Right? A lot of times it kind of starts as this like snotty looking stuff, and then over time it'll settle. All right, so an example of a precipitation reaction would be the combination of potassium chromate and barium nitrate. So these 2 species are going to react to form a precipitate. So again, you want to think of that from the context of like, okay, we have one container of potassium chromate, and we have another container of barium nitrate, and we combine those 2 containers and we have this precipitate that forms. So the big question is like, what happened? What chemical reaction took place? So this is the first time in this class where you will be given the reactants and you will have to tell me what the products are. So in order to get there, we have to take a step back and evaluate our reactants. So when we look at potassium chromate, if we were to write that species, it would be K2CrO4. You should be able to recognize that that is an ionic compound. And that, in conjunction with the first lecture of this chapter, should indicate to you that it might be a strong electrolyte. If it is a strong electrolyte, then we know that K2CrO4 in water is actually going to exist as 2K plus CrO4 2 minus. Right? That cation and anion pair are not so attracted to each other that they do not break up, right? So the introduction of water molecules is going to cause them to break apart, and you have this complete separation of those cation anion pairs. Now, barium nitrate, you should be able to recognize, is also an ionic compound, which means it also could be a strong electrolyte, which means that that homogeneous solution at the molecular level, contain two different species, the cation and the anion, interacting with water molecules. So if that's the case, and in fact it is, both of these species are strong electrolytes, and we'll see very soon how we can evaluate if they will or will not be broken apart in water or soluble in water. The question is, like, what is the identity of this? So we have our K plus our CrO4 plus our barium plus our nitrate, and those are all of our reactants, and they're all aqueous, right? All aqueous. And the question is, like, okay, what solid forms here? And the way we're going to answer that question is with a nice table from your textbook. So this table is of solubility rules, and if you've spent some time looking at the back of your periodic table, it should look pretty familiar. It's the table that's right above your common polyatomic ions. So this table you can think of as being divided kind of into an X or a cross. So the species above this line are going to be mostly soluble. The species below the red line are going to be mostly insoluble. Now, for both of these categories, there are going to be exceptions. Those exceptions are written in the second column. So here we have kind of our standard form, soluble versus insoluble, and then we have these exceptions that we need to take into consideration. So for instance, if we have a compound containing the alkali metal ions, which you should be able to recognize as group 1A, and they are contained, or they are combined with any other species, they are going to be soluble. Notice there are no exceptions. Nitrates, bicarbonates, and chlorates fall into the same thing. These are really good to take note of because we know if anything is paired with a 1A, it is not going to be insoluble, right? What does insoluble mean? Insoluble means that it is not soluble, which means that it is going to form a solid, which means that it is a precipitate. Same thing with nitrates, no exceptions, always going to be soluble. Now, once we get to this second section, we have halides and sulfates. Now, halides are generally, right, those are the halogens paired with something. Halogens are going to be generally soluble, but there are these insoluble exceptions. So normally when you see something with chloride, it's going to be soluble, like sodium chloride. We know that that is soluble. It's a strong electrolyte. But if that chlorine is paired with silver, mercury, or lead, it will crash out of solution and it'll form a solid. The same is true of sulfates, and its exceptions are written to its right. Now, the second half of our table kind of flips that. So on the left-hand side, we have insoluble, and on the right, we have these soluble exceptions. So first, we have carbonates, phosphates, chromates, and sulfides are generally insoluble. But notice if they're paired with an alkali metal or the ammonium ion, they are soluble. Which makes sense, that's a rule right here, right? Alkali metals, ammonia, soluble, no insoluble exceptions. Hydroxides are going to be insoluble unless they're with alkali metals and also the barium ion. So solubility rules are easy to use as long as you're familiar with this table. Some students don't like this table, so it's like hard for them to remember the exceptions, and it kind of flips meaning one column to the next halfway down. It isn't exactly the most user-friendly, so some students prefer this table. They have the same information, and I would just recommend to you to read both, and as you're working through recitation packets and other examples that I've given you, that you just see which one resonates the most with you, whichever one is the most intuitive, and use that on your quiz or exam. Okay, so these are the solubility rules. Let's go back to that example we had with potassium chromate and barium nitrate. Okay, so we have K2CrO4 plus we have our barium nitrate. So first, let's see if what I first said is correct, and these actually are electrolytes and they're going to break apart. So we have this chromate. Right, and chromates we can see down here are typically insoluble. The exception if they're with alkali metals or the ammonium ion, and potassium is indeed an alkali metal. So I know that this is going to be aqueous. So you want to write your state symbol behind your species so that you know that's going to be broken apart into its ions. Barium nitrate, remember nitrates was one of those that does not have an exception. And so what I just modeled for you is a really good approach as you're looking at these problems, is if you first look at your anion, that can be a helpful kind of starting place because that's how most of the table is set up. Exception being if you know it's an alkali. If it's a 1A, you know that it's soluble. You'll get the hang of it. Okay, so if both of those are aqueous, then we do have confirmation that yes, it's actually going to exist. And let me write our symbols, our state symbols. So the best representation of these two individual beakers being combined is written like so. I always forget my state symbols. Okay, so we know that a chemical reaction took place and that a solid formed. So the question is, what was that solid? And these reactions are always going to have the reactions that you are expected to evaluate are always going to be double displacement. Okay, so what does that mean? Let's give ourselves a little bit of room. Okay, so in a double displacement reaction, you're going to have this exchange of cation-anion pairs. Okay, so let's say in these double displacements, you have an initial cation-anion pair plus another cation-anion pair. Right, and we know that these are actually separated in solution, like our potassium chromate and our barium nitrate, if a precipitation occurs. Okay, so we had that cation and anion, and now because they're separate in solution, we have the opportunity for what I like to call a do-si-do. So what's happened here is these species were always separate in solution. So really we had cation plus anion plus our cation and anion of our other pair. And when they were in separate containers, that was fine. They were just floating around, separate ions, nothing doing except they can conduct electricity, which is pretty cool. And so the question here, and what we're demonstrating in that, and what's been demonstrated in that precipitation reaction, is this cation and this anion now have the chance to find each other in solution once you've combined those species. And so the question is, well, now that there's more charged particles in solution, is there the opportunity for new bonds to form? And will that cation-anion electrostatic attraction to each other be greater than the attraction of the anions to water? So yes, like dissolves like, but if those species are more attracted to each other, they're not going to break apart. If they don't break apart and they find each other by bouncing around their container and colliding with other water molecules and other ions, if we get this new pairing of cation and anion, is some new chemistry going to be possible? And what we saw in the last slide was that, yes, some new chemistry was possible with these species. So what exactly happened? So now we have this cation and this anion together for the first time. And we also had this anion and this cation together for the first time. So when you're evaluating these, you want to just say, okay, what would these new pairs be? So the new pairs would be KNO3 and our barium chromate, right? One cation with the other anion, so it's a do-si-do. And so now we want to look at our solubility rules and be like, okay, well, we know a precipitate formed, which one precipitated? Now, here we have an alkali metal and a nitrate, so we know that's aqueous. And here we have barium chromate, so we want to go back and look at chromates. Alkali metal or ammonium, that is not barium. Barium is not an alkali metal, nor is it ammonium. So this is going to be insoluble. And in fact, if we wanted to kind of reflect what's happening in solution again, because that KNO3 is aqueous, we could just write it as K plus aqueous plus NO3 negative aqueous plus our solid. You want to make sure that your equation is balanced, otherwise it's disobeying one of the laws of our universe. And here we have what is called our complete ionic equation, which is something that you'll see in your lab this week. Okay, so that's the evaluation process that we're going to go through. This is the new part of precipitation reactions. The rest of precipitation reactions, the evaluation, is just the same stoichiometry that we did in Chapter 2. The only difference between what you had to demonstrate in Chapter 3, and what you have to demonstrate now is now you are not going to be told what product forms. Instead, you have to answer that for yourself by evaluating these solubility trends. Ugh, that was an ugly highlight, huh? Okay, so bringing it back here, we just have a couple more slides and we're going to do a lot of examples, so don't get stressed. All right, so a nice kind of molecular diagram from your textbook shows chromate here. So that'd be the chromate. Oxygen is almost always drawn in red. Then we have our nitrogen, or our nitrate, excuse me. We have our potassium and our barium. So this is showing that initial combination of the species. They've just been added to that vessel together. We have the opportunity for them to find each other through random collisions with the container and other molecules. If we have a chromate and a barium crash into each other, we will have them precipitate out. And here you can see what that looks like after it's given time to rest. All right, so there's 3 different ways of representing these kind of reactions. The first is our formula equation. So the formula equation is what we've been doing this entire time, right? You can just think of that as your chemical equation. I very rarely call it the formula equation, but that's what it is. Notice that in this chapter, it is very important to keep your state symbols. So make sure that you're always paying attention to them. Like, we can look at this formula equation, and because whoever wrote this included state symbols, we know that a chemical reaction has taken place because our iron hydroxide, our iron 3 hydroxide, crashed out of solution. Our complete ionic equation is where you take that reaction and you expand it to more clearly show what has happened in your chemical reaction. So here we have our potassium and our hydroxide ions, our iron and our nitrate ions. All of our reactants are in aqueous form. Now they have the opportunity to make those new pairings, right? So our nitrate and our potassium can interact with each other, and our iron and our hydroxide can interact with each other. And we see indeed that iron hydroxide is going to crash out of solution. It is going to precipitate. Notice it's written as a solid and it's written together. Why? Because they're no longer aqueous. They're no longer free agents in solution. They've crashed out of solution together. However, our potassium and our nitrate are still just free in solution. So if you look at this, yes, our iron hydroxide underwent a chemical change. In contrast, our potassium nitrate did not. It always existed as aqueous ions, and it still does. These species that were aqueous as reactants and aqueous after the chemical reaction has taken place are known as spectator ions. The net ionic equation is just an abbreviated form of your complete ionic equation where you have omitted those spectator ions. It's always nice when going from complete ionic to net ionic to just, this is my approach, I put a box around the species that forms a solid. I underline the species in reactants that are represented in that solid. And then I just rewrite it. If I had a question of what are the spectator ions, my answer would be potassium and nitrate. Okay, the rest of this lecture is just going to be practicing. Okay. So first, let's just practice using this solubility chart and evaluating precipitation reactions to figure out what has precipitated. Okay, so here we have our, let me make this a little bit smaller for us so we can see where we're at. Yeah, you can still read that. Okay, so here we have our silver, if foreshadowing of things to come. Here we have our silver nitrate and our magnesium bromide. All right, so the first question is, are these both aqueous? Well, our state symbol is written for us, so we can be pretty confident that they are. So let's just go ahead and start expanding this formula equation to our complete ionic, right? So formula, this is just what we've been doing this whole semester, right? Just your regular chemical equation. We have our before we get that, our complete ionic. Which is going to be expanded to clearly show the species in solution, right? How they exist on the molecular level. Then our net ionic is going to omit spectator ions. Okay, so we have AgNO3. Nitrate, we know, is always going to be soluble. So that is not forming a solid, right? Soluble does not form a solid. Magnesium bromide. Bromide is a halogen. Halides of magnesium are not an insoluble exception. So we know that both of these species are going to exist as ions. We would write that as Ag plus aqueous, plus our NO3 aqueous, which is a negative charge. Then we have our magnesium, 2 positive aqueous, and our bromine, also aqueous. Okay, so now a chemical reaction has potentially taken place, maybe not, we'll find out. And so what we're asking ourselves is, all right, silver was paired with nitrate, it was soluble. Is silver bromine soluble? And is magnesium nitrate soluble, right? Doing a do-si-do, exchanging those pairs. So I'm just going to go ahead and write those options out. So we have silver bromide, and we have our magnesium nitrate. All right, so we have a nitrate. Nitrates are always insoluble, so I know this is going to be aqueous. So really I'm just looking at my silver bromide to see if it is aqueous or not. I find my bromine. Silver is an insoluble exception. If something is insoluble, that means it forms a solid. All right, so we're kind of running out of room, so I'm just going to rewrite these products as their complete ionic equations. So this would be AgBr solid, right? It formed a solid, so I'm going to keep it together. Our magnesium, however, is by itself an aqueous solution. You want to make sure that your species are balanced. It's a little easier to do when you're working with the formula equation. Right, so this would be our formula equation. Let me just move that so it's not confusing for you guys. So this is our formula equation. underneath that is our complete ionic equation. The formula equation right now is not balanced, so we want to go ahead and balance that. I forgot to make 2 of those. All right. So there's our formula equation and our complete ionic equation. Now we want to write our net ionic. So again, I like to approach this by just identifying what underwent chemical change. So it's nice just to start with your solid and then identify its parts. And then you just rewrite them. All right, so this is our what color haven't I used yet? Yeah, I can make that green. Net ionic right here. Okay, so those are the 3 kinds of chemical reactions that you'll be expected to write. We'll do another example of just finding those pairs and assigning solubility rules, and then we'll move on to some stoichiometry with our precipitation reactions. So let me just get rid of this. All right, so here we have KCl and PbNO3, so lead nitrate and KCl. First question we ask ourselves is, are these aqueous in solution? Do we have the opportunity for a do-si-do? Potassium is a 1A metal, alkali metal, so I know that that's aqueous. Lead nitrate, nitrate is always aqueous, so that's great. I know there's going to be this do-si-doing, so the question is, what happens if these 2 get together versus what happens when these 2 get together? So that would be the combination of PbCl2 and the combination of KNO3. Let's go ahead and balance that because it's an unbalanced chemical equation, and that's no bueno. So that would be 2. Annoyingly, there we go. That's a 2. I have to avoid that pop-up. So 2 KCl. 2 there, so I have 2 chlorines, I have 1 lead, I have 2 nitrates, I have 2 potassiums. All right, we're good to go. So this is our formula equation. And the question is, of this new cation-anion pairing, did I have something that would crash out of solution? So potassium, nitrate, going to be aqueous. But lead chlorate, let's find chlorine, halogen, lead is an exception. So that is going to be solid. So we would have 2 K plus aqueous plus 2 Cl minus aqueous plus 1 lead plus 2 nitrates. Oh, totally acceptable to squeeze in your symbols. Not acceptable to leave your parentheses. Going to our PbCl2 solid plus 2K plus 2NO3 minus aqueous. aqueous. Totally fair. All right, so this is my formula equation up